Okay, thank you. I just gave a training session, 1.5 hour. This is much shorter, and I'll just focus on the scientific component. The workshop was focused on how to access data. So if you later on, if you get interested to learn how to access and use data, there is a video recording where you can watch the how to access this OpenLandMap SolDB. So there is also a publication. It's still in review, so it's with a disclaimer. But there is on Earth System Science Data, there is a preprint of the publication that explains all the steps. I only have 20 minutes, but the paper is almost 40 pages. If you're more interested, you can zoom in and read more about this work. I've been in soil mapping and now almost 25 years. I mean, soil mapping. I'm like what Yufeng mentions, 30 plus. I'm the 50 plus now. So I've been almost 25 years. I did my PhD in pedometrics, and I made my first global carbon map in 2009, just for exercise. It was a 10 kilometer. Then I was behind this data set called Soil Grids. It's really my invention, and this publication we made 2016 made almost 4,000 citations. So I think it's people still cite it. And recently I wanted to restart that, and we went for really high resolution, and we are trying to map soil properties now at 30-meter global plus dynamic. It used to be static, static mapping, but now we're mapping it dynamic. So we created this framework. We call it EO Soil Mapper, but because the framework is mainly based on data from Landsat. So Landsat archive biophysical indices. We also have climatic time series data, and we have this 6 scales DTM from the previous presentation by Yufeng. So these are the main inputs. And here you see I spent years actually collating this point data and testing it and then binding it. And you can see these are the data with the physical and chemical soil properties. So this is about 250,000 samples with the soil carbon density, about 400, almost 500,000 samples with soil carbon content, and then about another 300,000 samples with soil pH. So there's a lot of data here, but it's clustered. You see Europe and US, parts of Brazil, parts of Africa. It's very clustered, and Russia, we have very little data. And also China, we had a gap. Now now we have a new data set from China we will add. And these are the soil types also. We use a USDA soil classification. So most of points are here actually. And so what we do, we do a space-time machine learning. So we overlay points. Once the points are prepared, we overlay in space-time. And then we use a scikit-map package maintained by my colleagues at OpenGeoHub, Leandro Davide, and we then do modeling and we predict all these maps. It's quite computational. It takes almost 10 days or something, or 14 days of computing, full capacity. So I'm talking about maybe 500,000 CPU hours of computing. So it's a serious task. And on the end, we produce the OpenLandMap SolDB. As I said, this is all possible because we spent about 3 years processing this Landsat. And I think Serkan has this paper on the mapping of the global GPP at 30-meter bi-monthly. And it was also, now we have with this Landsat archive that we've been, we got it about 2 years ago, right? And I think it's almost something like 12 papers already. We produce about 12 publications in 1 year, just practically based on this, having a possibility to process this Landsat archive. And it's just to visualize. So this is the original Landsat. That's what you get like NASA when it saves on the servers and stuff. But we need something like this because we need something that we can work with, right? And so we cannot work with gaps and clouds and things. So we need something like this, and that's this in this publication. That's what's been done by our colleague Davide Consoli and with Landro. They processed first Lanza to gap fill it, then we produced the GPP and number of other indices, and now we have a terabytes, hundreds of terabytes of data, which is really more like this, and that then also allows us to do soil mapping. So once we have this complete, consistent biophysical indices, we can do a space-time overlay, and we can see whether that correlates with the soil properties. And then the other thing, which is a big thing, what Yu Feng presented, the GDTM 30. So what is really special about it, that once you get a proper terrain model, you can derive hundreds of things. There's lots of information hidden in relief, but here is just a 15. We took about 15. Most important are like something like a hydrological indices, topographic wetness index, catchment area, but then also just this openness of terrain and things. So very interesting hill shading. And then Yu Feng really, he really worked hard. I have to say, I'm really proud of him. It's his first major work, and he really optimized it. And now I think it's a 2-day computing, and we can update it. So that's really amazing. And we produce everything at 6 scales. So it's so-called Gaussian pyramid. So you can see how the effect of this scale, I mean, at a different scale, different parameters, they can look very differently, especially hydrological parameters. So we know that from the predictive soil mapping that this scale can also have an effect. It has an also de facto effect on some soil forming process and things. So it's quite a complete picture now. And we had a team of at OpenGeoHub, I think about 7-8 people working on this global soil mapping. But most of work was I did most of work preparing the covariate layers and point data, and David and Shumong did fine tuning of models, and David did the final prediction. So we were like the core group, and then our colleagues also helped a lot, but a bit less here. And we also got the help from Travis Neumann, and he helped especially with checking the point data and harmonization functions. The biggest source of the point data is US, USDA, and USGS, almost like 40% of training points. So it's a bit of over-representation of US, but so it was very important to get the data, and we had many meetings, and we harmonized step by step. And also José Safanelli, originally Brazilian, but working at the Woodwell Climate Research. We worked about 3 years on making this open soil spectral library, and that's also kind of a basis for this Open Land Map SolDB. So he also helped a lot, José, so I'm really grateful, especially to Travis and José. And also, interestingly, when you look at the list of people, most of the co-authors actually are Brazilian. So the SolDB is really a Brazilian product in essence. So it's Samba based. These are the results. So we have quite some improvements in accuracy in comparison to previous attempts. This one on the left, you see this is just using stratified point samples and using out-of-bag samples. So these samples are not used at all in any training, any fine-tuning. This one is with the spatial blocking. So this is testing how much, if you move away 100 kilometers from the points, how well you perform. So you see the accuracy somewhere in between. This is a bit more pessimistic. This is a bit more optimistic. And this is purely temporal. So you don't use you take out the years. So you take all, for example, several years, and then you predict it from the neighboring years. So it basically matches a lot with the spatial cross-validation. So the true accuracy is somewhere in between this thing. In between is the true accuracy. Officially, we can say it's this one, but because the points are heavily clustered and there's a grouping of points, this is probably not realistic. It's only realistic for US and Europe. So in US and Europe, we could say this, but if we move to Russia or some places where very little points, then probably we are closer to this. So also very interesting variable importance. You know, we spend like a 1 year or something preparing this, and then to get all this thing, it takes like few hours, but then you get really excited. So we see for carbon, which is a big of high interest, so organic carbon density, we can see that this thing that we prepare, this Lanza data, it's paying off. So they do come up high. So lots of climatic layers come up, Chelsea climate and see. But we see the NDVI and GPP, which are also correlated between each other. They do come up high, so they're the highest. So that was quite a discovery. For pH, we can see also some Landsat bands, but we also see salinity grade, which makes sense. And we have the NDSI from the Landsat. So we see also geological material, the extent of karst. So that's important for pH. Also matches very well our previous knowledge of soils and pedology. And we have here so main big discoveries is that we find out that the GPPs, GPP NDVI, they're very high, and they are positively correlated. So the answer to people, it is a very significant result, really. But the answer to people is, they say, how do we improve the soil carbon? How do we improve soil health? So the answer that we get from this analysis is increase the GPP, and that means increase the primary productivity, convert to perennial systems, convert to grasslands, etc. And we think that's the way you can increase your soil organic carbon. And then also protect from deforestation, especially tropical peatlands, because a lot of soil carbon has been lost in tropical peatlands. Then we have a limited accuracy, so there's quite some uncertainty still, and to see some changes on a 5-year intervals is maybe difficult, but we do see for the land degradation processes, we can see distinctly there is a loss of soil organic carbon. So that's also good to see that these space-time predictions are actually, they can be used, so, but more for monitoring land degradation. And then the third one about soil pH, we see all these people using Earth observation to map salinity grade, etc. I think Giulio, you were maybe on this paper, no? Or was it Luis? Luis was in this paper. And so that also turns out to be a good product because it really helps with mapping soil pH. It was produced completely independently, and it looks like it helps with mapping the world pH, which is also good news. You see this uncertainty for soil organic carbon density. This is plotted on a log-log scale. When we look at this RMSC here, you know, the RMS is relatively large. So when I compare this RMSC with the average change in time of the soil carbon, then when it's the soil degradation, where you lose, for example, 12.5 ton per hectare at the 5-year period, then we can detect that. You see, we are here, we can detect it. That's the uncertainty now. But when you look at something more gradual, more gentle changes of like 2.5 ton per hectare, this one we probably we are not fit with this data set to monitor that fully, maybe some areas, but not fully. However, if you extend this to, for example, to 15 years, then we can also see even this conversion from cropland to grassland after 15 years, we will probably see in our predictions, it will be significant enough. This is this information, so like an information resolution or something. So you estimate your average error, and then your average error should be lower than the average change, you know, because otherwise you cannot quantify that change. And the data is now available on the app, so you can play with the data. The app is called world.soils.app. If you go there, you can see the data. You can click anywhere in the world, and the app will calculate. It's on top of the Google Earth Engine. So it will calculate the trends in pH for any point. You have a time slider. You can also open a soil carbon pH, soil carbon density. And also you can compare, you can do the slider, compare. You can also see where the training points are. You can see where the gaps are. And then you can also animate a bit. So you have these animations. This is a loss of soil carbon that we predicted due to deforestation and conversion of peatlands in Indonesia. So that's what we estimate as a distinct loss in soil carbon. And also we would like now people to send us more data, local data. It can be also local data. Then we would like to recompute and do reanalysis and then recalibrate. So this is a test where we really tested it actually. So we can see that locally we can then adjust our predictions. So they are consistent, globally always stay consistent, but locally they become more and more accurate. And this way we can update and make a better and better soil data for everyone. And with this thing, I finish my presentation.